Alright, so we'll begin the second half of the first homework assignment key on question 7. So, when Mary is 3 meters from the center of a merry-go-round, her tangential speed is 1.88 meters per second. What is her angular speed in radians per second? And B, what is the magnitude of her linear acceleration? Okay, so a couple things. Basically, this problem, make sure you're good with the terminology. Keep in mind that tangential means the same thing as linear. So when they ask us for what's her tangential velocity, we're looking for what is her linear velocity, which is our v. It's our good old traditional velocity that we're used to. Okay, so her tangential velocity is 1.88 meters per second. So we know her v is 1.88 meters per second. They tell us the radius. They tell us how far she is from the center of rotation, 3.00 meters. So then the question is, what is her angular speed? Well, we're looking for w. We're looking for what her motion is. And so just like we've seen a couple times now for linear distance to angular displacement, we want to make sure we're comfortable relating linear velocity to angular velocity. And the relationship for that is just v equals r times w. So then solving for this, we get 1.88 equals the radius 3 times, again, our omega. Solving for the omega, we get 0.627 radians per second. So part A, nothing too crazy. Again, the big relationship for any of our linear measurements, we can always relate our linear measurements to our angular measurements if we simply multiply by the radius. Okay, so that takes care of part A. Not too bad. Part B is where it gets a little bit trickier. Part B, making sure we're comfortable with the terminology and what is the magnitude of her linear acceleration. Well, there's actually two forms of linear acceleration. I know oftentimes for velocity and distance we're just worried about the one, but there actually are two forms of linear acceleration. There's the tangential acceleration, which relates to our radius times our alpha, but there's also, if we're moving in a circle, there's always the good old centripetal acceleration that we've seen before. Okay, so really we have to think about what happens with each of these, and then if both of them are present, you have to be comfortable enough to bring them together. Well, in this case, because she's moving at a constant tangential velocity, if she's moving at a constant velocity, right, if we know she's moving at a constant velocity, that tells us that the tangential acceleration needs to be equal to 0. Because she's not picking up any speed, she's also not slowing down. Okay, so we actually have this, which does simplify this particular problem a lot. I now know that I do not have to worry about the tangential acceleration, which means the only other form of linear acceleration that I have to worry about is my centripetal. So coming to my centripetal acceleration, I just simply use the equation. Centripetal acceleration equals v squared over r, so going back again to my 1.88 meters per second squared over the radius of 3 meters, and then I just have to solve for that. Okay, so when I do so, I get the centripetal acceleration to be about 1.18 meters per second squared. And again, this is a relatively simple case because we were able to cancel out the tangential acceleration. If we had a tangent acceleration present, we would have had to have done the Pythagorean theorem. But in this case, just roll through with the centripetal acceleration, and that'll be it for this. Our next example, a bicycle has wheels that are 60 centimeters in diameter, so our radius, of course, then is 0.30 meters. What is the angular speed of these wheels when it's moving at 4 meters per second? Again, this one's not bad at all. Just making sure we're comfortable with the relationship between linear, which they give us a linear velocity, and our angular velocity. So again, the relationship there, v equals r times omega. Our linear velocity, 4.0 meters per second. I know that that's my linear velocity since it does include the quantity of meters and not just radians per second. So 4.0 meters per second equals my radius of 0.30 meters times my omega, and then solving for omega, we get it to be about 13.3 repeating radians per second. So again, not too tricky with this one. Every once in a while there will be a problem, relatively straightforward, but obviously this one wasn't too tough. Next question, number 9. How long does it take for a rotating object to speed up from 15 radians per second to 33.3 radians per second? It has a uniform acceleration, so again, just constant acceleration of 3.45 radians per second squared. If we look through this, identify what we have our initial angular velocity, we have our final angular velocity, and we have our angular acceleration. So since we have three of those measurements all in the angular format, we actually are already good to go with kinematics. It's asking how long does it take, so we're looking for our time. So we're just going to choose which angular acceleration kinematics equation helps us find our time. And again, if we use our omega equals our initial plus alpha times t, we know three of those four quantities, so not too bad. So 33.3 equals 15 plus my alpha of 3.45 times t, and then it's just a matter of solving for t and watching your mathematics. I get t to be about 5.3 seconds. So solving that equation, just solving for t, and I find that time to be about 5.3. Our next question here, if you look at it, just looking at it, looks fairly intimidating, right? Okay, so kind of read through this and make sure everything makes sense in terms of what's going on. So a machinist turns on the power of a grinding wheel at a time 0 seconds. The wheel accelerates uniformly from rest for 10 seconds and reaches its angular speed of 96 radians per second. After reaching that speed, the wheels then run at that angular velocity for 40 seconds. Then the power is shut off. The wheel slows down uniformly at this angular acceleration until the wheel stops. For how long of a time after the power is shut off does it take the wheel to stop turning? And then part B, what is the total number of revolutions made by the machine from the time it was turned on until the time it stops? Okay, so part A really is just asking for the last portion of this motion. So if you read through this problem, there's really three stages. There's the first stage where it picks up speed, there's a second stage where it's moving at a constant speed, and then kind of the third stage where it's slowing down. The key to this problem is going to be breaking it up into those three stages. Part A is really just focusing then on the last stage, for how long of a time after the power is shut off. So that's once it starts to slow down. Okay, so let's just think for part A what measurements we know. Well, we know that it's slowing down with an acceleration of 1.5 radians per second. Because we do know that it's slowing down, we do know that acceleration needs to be a negative number, or at least if we're defining our initial velocity as positive. Since it is slowing down, it has to be in the opposite direction. We know that the wheel stops, which tells me my final angular velocity is 0. And then reading through this, just making sure we're comfortable with the fact that we know that it originally reached a speed of 96 radians per second. It ran at that constant speed, and then once it shuts down, that 96 radians per second is going to be our initial angular velocity. So again, if we kind of break this problem up for part A, it's not too bad, because you know three of your 4 or 5 kinematic variables, and since we have 3 variables, we can find either of the other 2. So in this case, it asks us for how long, indicating the time, so we just need to make sure we find our time of t. Okay, so like we've done a couple times before now, we'll just take our final acceleration, or excuse me, my final velocity equal to my initial velocity plus the acceleration times t, and I'll solve for t. Okay, so my 96, excuse me, that's actually the 0 on the left hand side, my final 0, 96 minus 1.5 t, and then I solve for t, and I get, should be somewhere about 64 seconds, so actually right at 64 seconds. So part A, making sure we understand kind of the context of the problem is the big hurdle to get through for part A, but not too bad to actually calculate. Part B is where it gets a little bit more challenging and not necessarily overly difficult, just several steps we have to do here. Okay, so they ask us to find the total number of revolutions made by the machine from the time it was turned on until the time it stops. So really what we need to do is we need to find the number of revolutions it makes while it's accelerating. We need to find the number of revolutions it makes while it's moving at a constant velocity. And we need to find the number of revolutions it makes as it's slowing down. Okay, so the key to this problem is break it up into 3 separate stages. If we can do that, if we can break it up into 3 separate stages, this problem is actually not too terrible. Okay, so let's actually start with the last stage since we still have all of those measurements up here. So if I want to find the number of revolutions it makes during its final stage as it's slowing down, I could just jump in with my theta equals my initial times time plus 1/2 alpha times t squared. So since I know all 4 of my kinematics now up above, I can pretty easily solve for theta. Okay, so that third theta would be my initial velocity of 96 times the time of 64 seconds plus 1/2 negative 1.5 times 64 squared. And obviously it is very important here, again, we do need to make sure the acceleration is negative so that we get the appropriate answer for this. Okay, so if I solve for that, I should get that to be about 3072. Okay, so this theta ends up becoming about 3072. So that's how many revolutions it makes then while it's slowing down. Excuse me, that's how many radians we make as we're slowing down. Okay, so then we need to still find our other two measurements here. So we still need to find how many radians we make as we're moving at a constant velocity, and we need to find how many radians we travel as we're picking up speed. Well, if we're starting with the beginning, so if we want to find how many radians we turn as we pick up speed, they give us the initial angular velocity of 0, they tell us the time is 10 seconds, and they tell us the acceleration, they tell us the final angular velocity is 96 radians per second. Okay. So then we just need to make sure we go ahead and solve for our theta. Now in order to get theta, you actually are going to have to solve for alpha first. Okay, so I'm going to need to use this relationship to solve for my angular acceleration. So I know my 96 equals 0 plus alpha times 10. Obviously if we solve through this, not too bad, just solving for alpha, we get that to be about 9.6 radians per second squared. And now that I have this, I can use basically the same relationship I just used up above to find my initial radians that I turn through. So my initial angular velocity of 0 times t plus 1/2. Now I know that this is 9.6 times t squared. So solving for that, I get this to be 480. Again, this represents not the number of revolutions, but the number of radians that we've turned through. So then I have one more final calculation to make, and this one hopefully is the easiest of the three. But for my final one, I need to find the number of revolutions it makes during that second stage of motion. But the good news about the second stage is it's moving at a constant velocity. And so if we come to our angular velocity formula and we just think of that as delta theta over t, if it's moving at a constant velocity, I can just use this. Since I know my velocity is 96, and I know that it's doing this for 40 seconds, I just take 96 equals theta over 40, and I solve for theta. And I get a relatively large number again, but it's about 3,840 radians. So at this point you have a couple of choices. You could either convert each one of these to revolutions right now. Since the question does ask us how many revolutions we've made, you could convert them first and then just add those revolutions up. Or I think what I'll probably go ahead and do is add up the total number of radians first and then convert those to the total number of revolutions. So to find my total, I'll then just do my 3,840 plus 480 plus my initial 3,072. Again, this will give me the total number of radians, which I find to be about 7,392 radians. And now that I have that total number of radians, to convert those to revolutions, I need to make sure I divide by 2 pi. Make sure, again, anytime we divide by 2 pi, throw out parentheses, just so we avoid those calculator errors. And we get our total number of revolutions to be about 1,176 revolutions. Okay. So part B here, obviously a number of steps involved, which makes it a little bit trickier. Definitely a lot of stuff going on, but as long as you can break it up into each of the 3 stages, it really does just boil down to kinematics. Okay, so making sure you're pretty comfortable with the kinematics, and then obviously making sure you're comfortable with the fine point that it's radians and not revolutions. Okay, so that ends then with this question here, question 10.